Grade 10 Chemistry. For this unit, Unit 3, Electrochemistry. In this video, we will go over Subunit 3.1 and introduce some general concepts about electrochemistry. So let's get started. Simply put, electrochemistry is the field of chemistry that deals with the relationship between electrical energy and chemical energy. It is concerned with the processes that bring about chemical reactions or changes to physical properties or chemical properties using electricity, or the generation of electrical energy from a chemical reaction. One of the core concepts in this field is that electrical energy and chemical energy are interconvertible. Based on this core concept of interconvertibility of chemical energy to electrical energy, we can look at the electrochemical cell, which is a device that converts chemical energy to electrical energy, or the inverse of electrical energy to chemical energy. Electrochemical cells are classified into two categories: electrolytic cells or galvanic or voltaic cells. In the case of electrolytic cells, we use electrical energy to bring about chemical changes, while in galvanic or voltaic cells, we convert chemical energy into electrical energy. Examples of galvanic cells include many types of batteries, and the reactions between the chemicals in these cells are responsible for the generation of the electricity. As we said before, electrochemistry is used in a number of industries. Electrolysis is used in the manufacturing of metals like sodium and aluminum, nonmetals like chlorine and hydrogen, and compounds like sodium hydroxide and sodium hypochlorite. We also use electrochemistry in the production of dry cell batteries and lead storage batteries in the automotive industry. Dry cell battery is typically made of a protective outer container, a zinc inner container, which acts as the anode, and a graphite rod, which acts as the cathode. In between the zinc and the graphite, there's a paste, which is made up of manganese dioxide, ammonium chloride, and carbon. So looking at this picture, we have a zinc outer case, which is the anode, and a graphite rod, which is the cathode. So in summary, electrochemistry is a field of chemistry that studies how chemical reactions can generate electricity and how electricity can cause chemical reactions in electrochemical cells. Electrochemistry deals with the relationship that exists between chemical energy and electrical energy, specifically the ability for chemical energy to convert into electrical energy, for electrical energy to be converted into chemical energy. And then finally, electrochemical cells include electrolytic cells and galvanic cells, which are also called voltaic cells. Explain metallic conductivity, explain electrolytic conductivity, and distinguish between metallic and electrolytic conduction. Beyond this, you should be able to distinguish between weak and strong electrolytes, and be able to use a conductivity apparatus to test the conductivity of substances. First, we'll go over a couple definitions. Electrical conductivity is the capacity of a substance to transmit electricity. And electrical conductors are materials that allow the passage of electricity through them. A conductivity apparatus is a device used to test the conductivity of different solid substances or that of aqueous solutions of different compounds. In Activity 3.2, you are asked to gather a number of common materials and determine whether they are conductors or insulators of electricity. Here in this diagram are some commonly found electrical conductors and electrical insulators. Among the conductors are metals such as silver, gold, copper, and steel, as well as seawater, which contains electrolytes. Among the insulators are rubber, glass, oil, diamonds, and wood. And we'll learn later in this subunit why these materials are unable to conduct electricity. One method that we can use to identify whether a material is a conductor or an insulator is to use something called a conductivity cell, diagram of which you can see here. The basic components of a conductivity apparatus include electric wires, electrodes, a DC source, otherwise known as a battery, a switch, and a light bulb. From the diagram, you can see that the anode and the cathode are placed on or in the material that we want to test. And if the light bulb turns on, we know that our material is a conductor because it is allowing the electricity to flow from the battery, through the switch, through the material, and back to the light bulb. So we only get a complete circuit if the material that we are testing is a conductor. So going into greater detail, electrical conductivity can be classified into two categories, either metallic conductivity or electrolytic conductivity, depending on the nature of the particles responsible for the flow of electric charges through the conductor. In metallic conductivity, this refers to the transmissions of electrical current through metals. And the transmission is directly related to the structure of those metals. In this case, the valence electrons in the atoms of the metal are bound very loosely to the respective nuclei and can move more easily through the metal. So to restate what was said on the previous slide, more simply, metals contain electrons that can move, and they're not in a fixed position. Those valence electrons are called free electrons, or mobile electrons, or delocalized electrons. And we can regard the structure of metals as a series of positively charged ions and a sea of negatively charged electrons. And you can see this in the diagram on this slide. So metallic conductivity is caused by the flow of those mobile electrons or delocalized electrons due to the repulsion exerted on them from electrons entering the metal from the source of the electricity. We can also call metallic conductivity electronic conductivity because the charge carriers in the metallic conductivity are electrons. Nonmetals are non-conductors of electricity because they do not have freely moving electrons. But there is one exception to this rule. So graphite is the only nonmetal which conducts electricity. You may remember from previous lessons that graphite is made up of carbon, a nonmetal. So the carbon atoms form layers with a hexagonal arrangement of atoms. And because of this arrangement, the electrons can move freely through the different layers, making graphite a good conductor of electricity. Now, in the earlier slide, we mentioned diamonds as an insulator. And if you remember from previous lessons, both diamonds and graphite are made from carbon. So we can look into this a little bit more to why diamonds are an insulator and graphite is a conductor. Substances that do not transmit electricity, either in solution or in a molten state, are called non-electrolytes. And some examples of non-electrolytes are ionic compounds when they're in a solid state, sugar, ethanol, oil, benzene, and liquid nitrogen. And you can see that all of these compounds, except for the ionic compounds in the solid state, all of the other ones have covalent bonding. Now we'll watch a video of an experiment where they use a conductivity cell to test the conductivities of a number of solids and also solutions. So as we saw before in the diagram of the conductivity cell, the light bulb will only turn on when the material that's being touched by the electrodes is a conductor, and that the electricity, meaning that the electricity can move through the material. So as a control, they take their conductivity apparatus and touch it on a metal table, and as expected, the light bulb turns on. Now we have distilled water, aluminum metal, sugar, salt, and also silicon dioxide, which is also known as sand. So only the aluminum was a conductor in that last trial. So now we're creating aqueous solutions. So you can see some of these materials do not dissolve. So now when they test the solution, we see that our sodium chloride is the only conductor in solution. Again, our control, light bulb turns on when it touches metal. So now we're testing some solids. And the only material that lights up in this case is solid copper. And again, we're creating some solutions. And now our calcium chloride and our cupric sulfate also conduct electricity. So in summary, electrical conductivity is the ability of substances to conduct electricity or for electricity to move through them. Metallic conductivity is the flow of electricity through metals, and the conduction of electricity through these metals is due to the presence of freely moving or delocalized valence electrons. Electrolytes are substances that conduct electricity, but only in aqueous solution or in a molten state. The conduction of electricity through electrolytes is due to the movement of anions and cations in opposite directions, and they are the charge carriers in this situation. Review question 1. Explain the difference between metallic and electrolytic conductivity. So in metallic conductivity, it's the delocalized electrons which allow for the flow of the electricity. Whereas in electrolytic conductivity, the ionization or the dissociation of anions and cations of the compound in either aqueous or molten form is responsible for the conductivity. Part 2. Explain the difference between electrolytes and non-electrolytes. So electrolytes dissociate to form cations and anions when dissolved in water or in their molten form, and non-electrolytes do not dissociate and therefore do not conduct electricity. So electrolytes conduct electricity because of their cations and anions, and non-electrolytes will not conduct electricity because they do not form ions. Review question 2. Why does sodium chloride and calcium chloride conduct electricity when they're dissolved in water or when they are in molten form, but not in the solid state? So in liquid and molten form, sodium chloride and calcium chloride can dissociate into the sodium and calcium 2+ and the chlorine negative ions. So it's the movement of these cations and anions in the fluid phases which allows for the conduction of electricity. In a solid form, the elements remain bonded through ionic bonding, and they remain in a crystalline structure. So the lack of charge and the rigid structure makes it so these compounds are non-conductors in solid form. Review question 3. Why are solutions of strong electrolytes better conductors of electricity than weak electrolytes? The reason for this is because strong electrolytes almost completely disassociate into their anion-cation forms, whereas weak electrolytes only partially disassociate. The more mobile cations and anions that you have available, the better conductivity that you'll have, and that's why strong electrolytes are better conductors than weak electrolytes. This concludes Unit 3.2. Thank you.